Welcome to G Fun Facts Online. Today, we're digging into a topic that's literally under our feet, but has massive implications for the air we breathe and our planet's climate. What if I told you that the very soil beneath us is cooking up a potent ingredient that's worsening air pollution? It sounds like science fiction, but it's real, and it's all about something called nitrous acid, or HONO. We all know about ground-level ozone, that nasty stuff that causes smog, harms our lungs, and even damages crops. For a long time, we pointed the finger mainly at cars and factories. But it turns out there's a hidden player, a natural source that's becoming increasingly significant. Nitrous acid released from soils. This isn't just a minor detail. It's part of a chemical feedback loop that can supercharge ozone pollution, especially as our world gets warmer and our farming becomes more intensive. So what exactly is this hidden culprit? Nitrous acid, or HONO as scientists call it. Think of HONO as a highly reactive gas. During the day, when sunlight hits it, HONO undergoes a chemical reaction called photolysis. This reaction produces something called hydroxyl radicals, or OH radicals. Now, these OH radicals are super important. They're like the atmosphere's primary detergent, breaking down all sorts of pollutants like volatile organic compounds, cells, and nitrogen oxides. But here's the catch. This breakdown process is a key step in forming ground-level ozone and other nasty secondary air pollutants. And get this, HONO photolysis can be responsible for a whopping 20 to 80% of all the OH radicals produced in the lower atmosphere during the day. That's a huge chunk. Now, where does most of this atmospheric HONO come from? You guessed it, the soil. It's estimated that soils can contribute up to 80% of the HONO found in the air in some places. But how does soil make HONO? It's a complex mix of microbial magic and soil chemistry. First, let's talk microbes. Soil bacteria, especially those that oxidize ammonia, are central to the nitrogen cycle. One key process is nitrification, where microbes turn ammonium into nitrate. Along this pathway, an intermediate called nitrite is formed, and this nitrite is a direct precursor to HONO. Another process, denitrification, which happens in low oxygen conditions, can also produce HONO. Once microbes have made nitrite, abiotic or non-living, processes take over. The nitrite can be converted to HONO and then released from the soil. A crucial step here is the protonation of nitrite. Basically, nitrite grabbing a hydrogen ion. This is heavily influenced by soil acidity, or pH. More acidic soils tend to be better at converting nitrite to HONO and letting it escape. If the concentration of HONO inside the soil is higher than in the air right above it, then out it goes, into the atmosphere. So HONO gets into the air from the soil. How does this amplify ozone? Well, once in the atmosphere, HONO, as we said, gets zapped by sunlight to form those OH radicals. These OH radicals then act like accelerators for the chemical reactions that turn nitrogen oxides and VOCs into ozone. HONO essentially gives the ozone-making machinery an extra, powerful kickstart. This is where the term feedback loop comes in. Factors related to climate change can boost HONO emissions, which then create more ozone. And ozone itself is a greenhouse gas, contributing to further warming. For instance, rising global temperatures, a hallmark of climate change, can supercharge microbial activity in the soil and change soil moisture levels, leading to more HONO production and release. More HONO means more ozone, which means more warming. It's a cycle. Several factors can turn the dial up or down on how much HONO our soils release. A huge one is nitrogen input, especially from fertilizers used in agriculture. When we add nitrogen fertilizers, we're giving those soil microbes more raw material, ammonium, boosting nitrification and the amount of nitrite available to become HONO. Ammonium fertilizers, in particular, are known to significantly crank up HONO emissions. Soil temperature is another biggie. Warmer soils mean more active microbes and also mean HONO is less likely to stay dissolved in soil water, making it easier for it to escape as a gas. That's why global soil HONO emissions often peak in the summer. Soil moisture is also critical, though it's a bit complex. While some studies show high HONO emissions in drier soils, others have found significant emissions even when the soil is quite wet. It seems the very top layer of the soil might be the key. If it's drier, HONO can escape more easily. Rapid evaporation from the soil surface, driven by temperature and humidity, can also enhance its release. Then there's soil pH. Acidic conditions generally favor HONO formation from nitrite. However, even neutral or alkaline soils can be significant HONO sources if they have high nitrite concentrations. And things like soil type, how much organic matter it contains, and how much oxygen is available also play their part. The scale of this problem is pretty significant. Research shows that global soil HONO emissions jumped from about 9.4 teragrams of nitrogen per year in 1980 to 11.5 teragrams by 2016. These emissions are estimated to increase global average surface ozone levels by around 2.5% annually. That might not sound like much, but locally, especially in farming regions, these emissions can boost daytime ozone by 8% or even up to 29% in some hotspots. This extra ozone is bad news for us, causing respiratory problems, and it's also bad for plants. It can damage vegetation, reduce crop yields, threatening food security, and make plants less efficient at soaking up carbon dioxide. Interestingly, the impact of soil HONO is even more pronounced in areas where the air is already relatively clean from industrial and traffic pollution. In these NOx-limited zones, any extra nitrogen compounds, which HONO contributes to, can lead to a bigger jump in ozone levels. So as we clean up our cars and factories, this soil source becomes relatively more important. Recent research, like studies from the Hong Kong Polytechnic University, has been crucial in understanding this. Scientists are using extensive datasets of soil HONO measurements from all over the world and plugging them into advanced climate chemistry models. These studies confirm the rise in soil HONO emissions, linking it strongly to increased fertilizer use and climate change factors like warmer soils and changing moisture patterns. They're also mapping out seasonal and geographic variations, sometimes finding emission peaks in summer during crop growing seasons. And they're even identifying other HONO sources, like livestock farming, and using sophisticated techniques like isotopic fingerprinting to tell different sources apart. So what can we do about it? Understanding this soil nitrous acid feedback loop actually opens up new ways to tackle air pollution. A major focus is on optimizing fertilizer use in agriculture. This means things like placing fertilizer deeper in the soil to reduce surface emissions, using nitrification inhibitors, chemicals that slow down the conversion of ammonium to nitrite, and being smarter about the timing and amount of fertilizer applied so it matches what the crops actually need. Sustainable land management practices, like using cover crops, can also help. Some cover crops can soak up excess nitrogen, while others can provide nitrogen more slowly and naturally. And of course, we need to keep improving our climate and air quality models to accurately include soil HONO emissions. We also need more on-the-ground monitoring to really understand what's happening in different ecosystems and with different farming practices. Digging deeper into the specific microbes involved could also lead to more targeted solutions. In conclusion, the discovery of the soil nitrous acid feedback loop really highlights how interconnected everything is in Earth's systems. What happens in the soil doesn't just stay in the soil, it dramatically affects the air we breathe and the climate we live in. As we successfully reduce pollution from traditional sources like factories and traffic, the relative importance of these natural but human-influenced sources like soil HONO is only going to grow. So, including soil HONO in our air pollution control plans and climate strategies isn't just an idea anymore, it's a critical step for cleaner air and a healthier planet. It's a complex challenge, but one that demands our attention through smart farming, continued research, and integrated environmental policies. That's all for this episode of G Fun Facts Online. Thanks for tuning in, and remember, there's a whole world of fascinating science happening right beneath our feet.